This is the first of a series of lectures on distributed abstraction and the algorithm for implementing the abstractions in various models. And it will be about reliable broadcast. We will start where we stopped in the last lecture and remind ourselves with the various models of distributed algorithms. We will discuss briefly general guidelines for designing algorithms in the various models. So if we remember, we had the fail-stop model, the fail-silent model, the fail-noisy model, and the fail-recovery model. So let us go through each one of these models again. In the fail-stop model, we have a crash-stop process model, where a process becomes faulty by stopping, that is a crash, and it stops from there on taking any computation steps. We normally use perfect links or reliable links. Actually, we don't use any FIFO links in this chapter. We will use FIFO links later in one of the algorithms. And we assume, of course, that we have a perfect failure detector. Therefore, we are in the synchronous model. So in this model, local algorithm executing on each process can track the set of correct processes. And that means that without violating any liveness property, the local algorithm can use techniques based on request and reply. A process can send messages to everybody and waits for replies from the set of alive processes. So techniques based on acknowledgement from all the set of correct processes are quite common in these algorithms. Then we have the fail-silent model. And in the fail-silent model, it is a crash-stop process model with perfect links, but we are in the asynchronous distributed system model where we have no timing assumptions and therefore we have no access to failure detectors. Algorithms in this model normally assumes that a majority of processes are always correct. So the algorithm works as long as a majority of processes are always correct. And it often uses a technique called the majority quorum, which we will discuss in the next unit. When you write an algorithm for this model, the local algorithm in each process cannot wait for more than the majority of processes. So, for example, if you have 5 processes, it waits for 3 processes. Otherwise, it might get stuck. If it waits for more, then some of the processes might have failed and violate some liveness property. Then we have the fail-noisy model. In the fail-noisy model, we have a crash-stop process model. We have reliable, perfect links, and we use the eventually perfect failure detector, diamond P. And here we are in the partially synchronous model. So in general, to guarantee safety property, any algorithm has to assume that the failure detector is inaccurate. Because if it does not assume that, it might lead to a bad event. And a bad event will violate safety forever. Eventual accuracy is only used to guarantee liveness. Finally, we will have the fail recovery model. It is a crash recovery process model, and we have stubborn links or persistent links like logs that log all messages. So this algorithm relies often on a persistent memory to store and retrieve critical information. After recovery, a process may contact other processes to retrieve up-to-date state information. Some algorithms relax the reliability condition on links and channels, and allow message loss, duplication, and reordering. And these algorithms are quite easy to implement then in the fair recovery model because it does not require any stubborn link or a persistent log.